Hello everyone, welcome to the second week of the supply chain design course. And for this week, we will jump to the second chapter, which is about inventory management. Okay, so here is the outline of the chapter. So in the first session, we will get acquainted to the concept of inventory, which some of you might be familiar with. And then in the second session of the chapter, we will explore the EOQ model. In the third session of the chapter, we will um, explore the effects of demand uncertainty, in which there are multiple models for inventory management that we will have opportunity to get familiar with. And in the fourth section of the chapter, we will explore the concept of risk pool, um, as well as the centralized and decentralized system. Um, the next section will be about managing inventory in the supply chain, and the last session of this chapter will to summarize several points about demand forecasting, which all of you has a chance to study in the other course. Okay, let's get started. What is inventory? So inventory is stock of item kept to meet future demand, and it has three forms. The first one is raw material inventory, and the next one is work in process inventory, and the last form of inventory is finished product or finished good. So here is the chart, the figure for you to understand the difference between these three forms of inventory. So basically, they are classified um, based on different stages in production. So raw material um, is components that necessary for the production, and work in process is actually happening or produced during the manufacturing, and the finished goods are actually the final product that will be shipped to the end use customer. And the objective of inventory management is to strive a balance between inventory investment and customer service. So the next question is, why do we need to hold inventory? We categorized the reason for this question into the four main causes. The first one, lead time, uncertainty, short product life cycle, and economies of scales. Okay, so we will go with the first cost, the lead time. As you might know that the inventory exists in three forms. And the first form is raw material. And the raw material usually shipped from multiple supplier, right? So basically they will have different replenishment time. So for example, your iPhone will have several components such as the case or the mainframe or the screen, and these components will be shipped from different suppliers, and each supplier will have different replenishment time. Maybe your case come after several days, but your screen will arrive in several weeks. So because the different lead time, and for you to start your manufacturing stage, you need to keep inventory of these different components in your warehouse. Okay. The second cost, uncertainty. Uncertainties here is understand as the mainly from the market because as you might know from the demand forecasting cost, there is nothing certain about the market demand. For example, during this disease outbreak, COVID-19, right? All the demand has been, the demand of most of the product has been decreased sharply, but the demands for the personal mask as well as for the sanitary gel has been changed substantially. Okay, so because of the demand uncertainty, we need to hold inventory to fulfill the customer demand once the customer demand surge or increase sharply. Okay, so the next one, short product life cycle. As you can see that because of the um, Industrial Revolution 4.0, all the product has shorter life cycle. For example, in the past, you can buy one phone and use it for, I mean, for example, in the past, you can buy one Nokia and use it for 5 to 10 years. But now you spend more money for your iPhone or your Galaxy, but you will have demand to recycle it or replace it after 1 or 2 years. It means that the product life cycle has been shortened. And in order to which also make the demand uncertainty more um, drastically drastical. So that's why because of the short product life cycle, we need to hold the inventory. And the next one is economies of scale. Economy of scale can be understood as the more you buy, the cheaper you get. Okay, so for example, for one manufacturing producing one product will occur some fixed cost like the setup cost for their assembly line, right? And that fixed cost also occurred when that manufacturer produced 1,000 items. So instead of producing one item, the manufacturer will consider producing 1,000 items so that he can save the units cost per item. Okay, and that's what we call the economies of scale. And because the manufacturer produced 1,000 items to save the production unit cost, he need to keep those 1,000 items that he just manufactured in the warehouse to wait for those items to be sold, right? Okay, so we will move to the next part, which is about the EOQ model, one of the most solid model in the inventory management. So the EOQ stands for economic order quantity. It is the order quantity that minimizes the total holding cost and ordering cost. So for this EOQ model, we will have several primary assumptions. The first one is demand is constant at the rate of D items per day. And we will have the fixed order quantity Q item per order. And the fixed cost or the setup or ordering cost CP is incurred when an order is placed. Um, we also have the holding cost CH occurred per unit held in inventory per holding day, and we do not consider the lead time in this model, as well as assume that the initial inventory will be zero. And for this model, we will assume that the planning horizon is infinite. It means that there is no limitation for the planning horizon. Okay, so for you to better understand this EOQ model, please look at the figure here. So here, the vertical axis will be the inventory level, okay? And the horizon axis will be the time. And this log represent one the usage rate, okay? And the distance between two vertical line will be a circle time t, okay? So in general, at the beginning of one circle, the initial inventory will be zero, okay? And that's when you need to make an order. And because the lead time is zero, it means that as soon as you place an order, you will get it immediately. So you will order at the quantity of Q. So that's make your maximum inventory level here will be Q. Okay. And because we have the usage rates, which is the demand, the daily demand is constant. So that's why we have the graph here as the linear one. Okay. So at the beginning of the of one circle time, you will have the inventory level at Q. And by the end of this circle time T, your inventory level will drop to zero. And because it will take no time for you to get a new order. So that's why at this point, by the end of one circle, your inventory level will jump to Q, okay? After you place a new order. Okay, so because the maximum inventory level is Q and the minimum one is zero, so we have the average inventory on hand will be equal to the average of the maximum and the minimum, which is Q divided by 2. Okay? So the inventory cost in one circle will contain the ordering cost, CP, plus the holding cost. So the holding cost here will be equal to the unit holding cost multiple the cycle time T and multiple the average inventory on hand. Okay? And the demand in one circle, of course, it will be equal to Q, equal to the your order quantity, as well as we can calculate this as the formula T multiple D, time multiple unit demand. Okay, so the objective for this EOQ model is to minimize total cost. So here we have the total cost will be made up with the setup cost or the altering cost. Okay, so it will have the shape like this. And for the holding cost here, please note that for the holding cost, it will be a linear model for the Q, for the order quantity. Okay, so that's why we will have a linear graph here. And this is the total cost of holding and ordering cost. Okay, so in order to calculate the average inventory per day, we just simply divided the inventory cost here divided by T. Okay, well, I'm sorry, this should be the average inventory cost per day. Okay, so just remind that because Q equal to T multiple D, so we can replace T here by Q divided D. Okay, and in order to calculate the minimum the optimal total cost, what should we do? We will take the first order of this function according to Q. Okay, and then we will get the optimal order quantity Q star as the square root of 2 CPD divided by CH. Okay, so let's jump to one example for you to better understand this EOQ model. Okay, so here we have the demand 2000 unit and the ordering cost $20 per order, and the inventory cost will be 0.5 per unit per year. And note that here the unit time will be in annual. Okay, so your job for this one will be to determine the optimal number of needles to order. Please pause this video and calculate yourself so that you can better understand the EOQ model. Okay, so in order to calculate the optimal number of needles, it's real simple. All you have to do is just plug the value into our formula of the EOQ model. So here we will take the square root of 2 multiple the the ordering cost, which is 20, multiple the demand, which is 2000, and divided the holding cost, which is 1.5. So we will get the optimal number of needles to order will be 400 units. Okay, so the next question, calculate the expected number of order per year. And how can we do that? Please pause this video and calculate yourself. Okay, so as you might see that in a year, this manufacturer will face the total demand of 2000 units. Okay, and for every time he just order 400 units. So it means that in order to calculate the expected number of orders per year, we will take the demand, the annual demand, divided by the order quantity. So we will get 5 orders per year. Okay? The next question. Determine the length of a cycle time, assuming that there are 250 working days per year. Please pause this video and calculate yourself. Well, actually, what they require us to calculate here in this question is to calculate T, right? And as you can see that in 1 year, we will make the expected number of orders as 5, okay? And we have 250 working days per year. So it means that for every 50 working days, we will make an order. That's the length of a cycle time. And the last question for this example is to calculate the total annual cost, TC. Please pause this video and calculate yourself. Okay, so in order to calculate the total annual cost, we will calculate the annual holding cost plus annual ordering cost. In terms of the annual holding cost, we will have the unit holding cost multiple the average inventory level over a year. And as you can see that because, let me come back to our graph. Because for each cycle time, our average inventory on hand is Q divided by 2, right? Half of Q. So that's why for a year, for multiple T, the average inventory on hand will always be Q divided by 2. That's why for the annual average inventory level, we also get Q divided by 2, okay? And for the annual ordering cost, it will be much easier. It will be the ordering cost for each order multiple the number of orders that you will make in a year. So in general, the total cost for a year will be 200 for this example. Okay? And please, if you have any question, related to this example, you can post this in the discussion and I will be gladly answer you as soon as possible. Okay, so what can we conclude about this EOQ model? The EOQ model is robust, illustrating the trade-off between the setup cost and inventory holding cost. It means that this EOQ model is widely applicable in many areas, many industry. Okay, and the second one is the total cost is insensitive to order quantity. And in order for you to better understand the second statement, let's come back with the example. So we will calculate the total annual cost when the actual EOQ for the new demand is 500 units. So we have the demand 2000, the setup cost will be $20 per order, and the holding cost is $0.5 per unit per year, and the Q here is actually 500 units, and still the same 5 order per year, and T will be 50 days. So all you have to do is just to plug values into the formula, and we will get the TC here is the new total cost will be 225. And as you can see that the total cost increased by only 12.5% from 200 to $225 when the order quantity is up by 25%, and the last order quantity is 400. The new order quantity is 500. So it means that the order quantity is up by 25%, but the total cost increased by only 12.5%. So that's why we conclude that the total cost is insensitive to order quantity. Okay? Okay, so let's jump to the next session, the effects of demand uncertainty. So demand uncertainty, as its name, demand is always uncertain, but most companies treat the word as if it was predictable. Production and inventory planning are based on forecast of demand made far in advance of the selling season. And if you have any chance to go internship or to observe the demand forecasting of several companies in Vietnam, you can see that they usually make the demand forecast at the beginning of the year or the beginning of one quarter. Okay, and the sharp product life cycle add more uncertainty, which I already explained in the last session of this chapter. So, can you recall several rules of thumb for demand forecasting? Think about it. Let's pause this video for several seconds and think about several rules of thumb for demand forecasting. Okay, so we have three main rules of thumb for demand forecasting. The forecast is always wrong. And the longer the forecast horizon, the worse the forecast. It means that if you make the forecast for 1 year, it will be worse than the forecasting for just only 1 month. Okay, aggregate forecasts are more accurate. It means that if you have several product lines and you make the demand forecasting for total product lines, it will be more accurate than forecasting for just only one product line. Okay. Okay. And because of the demand uncertainty, so we have to evolve the EOQ model into the other model so that we can adapt with the demand uncertainty for the sake of inventory management. Okay, so the very first model for single period, I'm sorry. So the first model for the demand uncertainty will be single period model. Okay, so for this model, the assumption will be the product has only uh, one ordering opportunity because the product has really short life cycle, and this can be applied into the fashion industry. Okay, so for this single period model, we will consider the snow time example. And for these examples, they have the new design completed and one production opportunity. Based on the past sales, knowledge of the industry, and economic condition, the marketing department has a probabilistic forecast, and the forecast is illustrated in this graph. So here they have six different scenario, six different demand scenario, and each will have the probability of occurrence. So for example, um, for the demand scenario of 8,000 unit, the probability will be around 11%. Okay, and for the 12,000, the demand scenario of 12,000 unit of sales, the probability will be 28%. Okay, and etc. And we have all the necessary parameter here, including the variable cost. The variable cost will be the cost that varies along with the production unit. So it means that the more units that you produce, the more variable cost. Okay, the selling price P at 125 per unit. The fixed production cost is $100,000. Okay, so the fixed production cost here is the cost that will be fixed, that will be independent from the number of from the production quantity. So it means that no matter how many units that you decide to produce, it's always cost you $100,000. And for the salvage value, the salvage value for excessive inventory will be, will be the sale off price by the end of the selling season. Okay, so during the selling season, you can sell your product at $125 per unit, but by the end of the selling season, you need to lower your selling price at the sale off price of $20 per unit. Okay. Okay, so Georgia will be to calculate the snow time profit in the following scenario. So in the first scenario, suppose that you will make 12,000 jacket and demand will be end up being 13,000 jacket. Okay, so it means that for the first scenario, you will produce less than the demand, the real demand. Okay, and in the second scenario, you will produce more than you can sell during the selling season. Okay, so please pause this video and calculate yourself first. Okay, so in general, we will have the formula for the profit will be equal to the revenue during the selling season minus variable cost minus fixed cost and plus salvage, which is the revenue from the sale off. Okay, so for the scenario one, we will have the revenue coming from 12,000 units that we produce, right? And because we only produce 12,000 jacket, so the variable cost will be the cost for this 12,000 jacket, and the fixed cost $100, $100,000, which doesn't change for any scenario. Do we have the salvage in this scenario? No, because in this scenario, you produce less than the less than the market demand. Okay, so we will have the profit at $440,000. How about scenario two? Scenario two, because you only sells 11,000 jacket, right, from the market demand. So that's why the revenue that you can get is from this 11,000 unit of market demand. But you have to pay the variable cost of 12,000 because you decide to produce as 12,000 unit minus the fixed cost. And in this scenario, we will have the salvage value, which is 1,000 left, right? Because during the season, you only sell 11,000, but you produce 12,000. So by the end of the selling season, you have 1,000 left. So this will be your salvage value. And then your profit will get for this scenario will be $335,000. Okay, and if we keep doing that for all the demand scenario, you can see that the profit, the weighted profits as per the demand scenario illustrated as this figure. So based on this figure, what is the optimal quantity for the snow time to produce? It will be around 12,000, right? 12,000 and around 12,000 and 12,500. Okay, It will be around that. Okay, so it means that the optimal order quantity is not necessarily equal to the average demand. Okay. Okay, so we will move to the next part of the model for demand uncertainty, which is the multiple order opportunity. So in this one, we will need to define the concept of initial inventory. So if you recall the EOQ model, they assume that the initial inventory at zero, okay? But for this multiple order opportunity, we will consider the initial inventory. And this initial inventory can be used to meet the demand as well as to avoid fixed costs for a new order or for the production. Okay, so if the single order opportunity is for fashion industry, the other industry can repeatedly order product at any time during the year. And they also have to wait for a delivery lead time to have his order fulfilled. Okay. And for this multiple order opportunity, we will consider the continuous review policy. We will consider two types of inventory policy. The first type is continuous review policy, and the second one is periodic review policy. So for the continuous review policy, inventory is reviewed continuously. It means that the inventory can be reviewed at any time. Okay, and an order will be replaced when the inventory reaches the reorder point. And for the periodic review policy, the inventory is reviewed as regular interval and an appropriate quantity is ordered after each review. Okay? So for the periodic review policy, inventory can be reviewed once a month or twice a month or once a week or once a quarter. It depends on the characteristic or the nature of the product that the periodic review policies is applied. Okay. Okay, so there is one question for you to think about, and I will definitely put it in the homework. Which type of inventory policy is more popular in reality? Okay, and for you to better imagine what it means in Vietnamese, continuous review policy mean kiểm kho liên tục ha. And periodic review policy means kiểm kho định kỳ. Okay, so the question is which type is more popular in reality and why? Okay, so we will approach the first type of continuous review policy. So for this policy, it will be based on several assumptions. The daily demand is random and follow a normal distribution which is characterized with the average demand AVG and the standard deviation STD. Okay. And if you can recall the normal distribution, it will have the bell shape. Okay. And when an order is placed, there will be a fixed cost CP and the holding cost CH per unit held in the inventory per unit time. And for this model, we also consider the lead time to fulfill the order after the order is placed, L, and L here is different from 0. Okay, the distributor will commit a service level alpha, and alpha here implies the probability of not stocking out during lead time. And we will consider the inventory position equal to actual inventory plus item already ordered but not delivered minus item back order. Back order here can be understood as the item that the customer the customer place but not available, so the customer have to wait until their product, their wanted product, come back to the seller's warehouse, um, something like that. And if you has been shopping with Tiki, back order here is equivalent to the email me when this product is stock. Okay. And the continuous review policies is known as the QR policy. Q here is the order quantity, and the R here is the reorder point. Okay, so the R here, the reorder points, will have two components. The first components of the reorder point account for the average demand during the lead time, which can be calculated as L multiple the average demand. Okay, and the second component account for deviation from the average, which we call safety stock, and is can be calculated as Z multiple standard deviation of demand multiple square root of lead time. And Z here is referred as the safety factor to ensure that the probability of stocking out during lead time is exactly 1 minus alpha. Okay, so in general, the formula for reorder point R will be equal to the average demand during lead time plus safety stock. So as you can see that here is the inventory level in the QR policy. So the vertical axis will be the inventory level, and the horizontal axis will be the time. Okay, so the maximum inventory level will be equal to Q plus R, which is the sum of order quantity and reorder point. Okay, so because the demand varies during the cycle time. So it means that we do not have the linear graph here for the usage rate. Okay. Okay, so consider it. So when the inventory level drop to below the reorder point, that's when we should start placing a new order. Okay, and here is the lead time. The lead time here is the time that we have to, is the period that we have to wait for our order to be fulfilled. Okay, so during lead time, I'm sorry, lead time is here. So during lead time, the inventory levels keep decreasing, but we still have the safety stock here to cover the demand during lead time, right? And after lead time, we will get our new order, which which make the inventory level up at a quantity of Q. Okay. So the inventory level before receiving an order will be equal to safety stock, right? And the inventory after receiving an order will be equal to the safety stock plus our order quantity. So that's make the average inventory level will be equal to the average of this one and this one. So that's why we get the average inventory at Q divided by 2 plus safety stock. Okay? Okay, so let's recall that here is the reorder level. Reorder level contained two components. The first component to account for the demand during lead time and the safety stock for deviation of demand during lead time. And the order quantity, I'm sorry, Q here is actually, no, the order quantity here, Q here, will be equal to the square root of 2CP multiple average demand divided by CH. Okay, so this is the average inventory. And this is this table for service level and service factor, Z. Okay. Okay, so the last part of this week is to apply what we have learned about the continuous review policy into this example. So for this example, we have one distributor of TV set trying to set inventory policy for one of his TV models. And there will be a fixed ordering cost of $4,500, and the cost of a TV set is 250. The annual inventory holding cost is about 18% of the product cost. Replenishment time is about 2 weeks. And we have the table provide data on the number of TV sets sold to the retailer in the last 12 months. If the distributor would like to ensure the service level of 97%, what should be the reorder level and the order quantity that the distribution should use? And we assume that there is 30 days in a month and 55 weeks in a year. Okay, so please pause these videos and then calculate by yourself first. Well, the very first thing that you can get from the historical data is to calculate the monthly demand as well as standard deviation of monthly demand. And the average of monthly demand here is around 191 TV set, and the standard deviation of monthly demand is around 66. But one thing that you need to keep in mind when you solve this type of problem is that you need to align all the unit. So here, the demand you have is in month, but the lead time is in weeks. So that's why you need to transform the average and the standard deviation into weekly values. Okay? You can just simply transform this lead time into month. Okay? So if you transform the average demand into week, because we have in a month you have 30 days, so it will be equal to 4.3 weeks in a month, right? So that's why you can calculate the average, the weekly average demand at 44. And the standard deviation will be equal to the standard deviation of monthly demand divided by the square root of 4.3 weeks per month. Then you can get the standard deviation of weekly demand at 32. Alpha equal to 97%, it means that we can have the safety factor at 1.88. And the annual holding cost, because it will be around 18% of the product cost, which is 250. So the annual holding cost is $45. And still, you need to transform this annual value into weekly value, okay? And so you can take the annual holding cost divided by 52 weeks a year. So you can get the weekly holding cost at 0.87. Okay, so now your job will be easy. Just plug in. So the order quantity, as we calculated here, is 679. And the reorder point will be around 176. Okay, so I think we will wrap up everything for this week. See you next week, and we will continue with chapter 2. Okay, thank you for listening.